Entropy and the second law of thermodynamics have predicted some of the most important aspects of nature. From defining the arrow of time, predicting the ultimate heat death of universe, and providing the driving force for the development of structure as well as decay to the randomness of the universe. But what is entropy and how fundamental is it to our universe? Entropy is surely one of the most interesting and misunderstood concepts in all of physics. According to the second law of thermodynamics, the entropy of the universe must always increase. It's a law that seems emergent from deeper laws. It's statistical in nature and yet may ultimately be more fundamental and unavoidable than many other laws in physics. In 1824, Sadi Carnot published his reflections on the motor power of fire, in which he revealed the theory of perfect engine efficiency. Heat engines, which in Carnot's day were the steam engines, work by turning the flow of heat energy into mechanical energy. For heat to flow, we need two reservoirs of different temperatures. A perfectly efficient engine undergoing the Carnot cycle converts all transferred heat energy into useful work. In principle, the work can then be converted back into heat, and so the temperature differential can be re-established. However, an inefficient engine will slowly deplete the difference in temperature, reducing the heat flow, and the engine slows down. Around a half century later, Rudolf Clausius was inspired to quantify this tendency of heat engines to decay over time. This is where the idea of entropy came into picture. Clausius defined entropy as the internal property that changes as heat energy moves around within the system. Specifically, the change in entropy of each reservoir is the heat energy that go into or out of that reservoir divided by its temperature. For a Carnot cycle, the overall change in entropy is zero, but for any less efficient cycle, entropy increases. In fact, an increase in entropy means that the heat reservoirs are approaching the same temperature, reducing the capacity to do useful work. Clausius and Carnot's work revealed entropy is a measure of how evenly spread out a system's energy is. The more evenly spread, the less useful the energy. For an isolated system, the best we can hope for is that the separation of energy and the entropy remain constant. In reality, it will almost always increase unless energy comes in from the outside to re-establish the temperature differential. This understanding of entropy is in terms of flowing heat, and it came from the days when many, including Carnot himself, believed that heat was a physical fluid called caloric. It took a whole new concept to understand the reality of entropy, and that concept was statistical mechanics founded by the great Ludwig Boltzmann with his kinetic theory of gases. This theory explained thermodynamic behavior as the summed result of the individual motion of tiny particles under Newton's laws of motion. StatMech is really astounding, and it's founded on an absurdly simple idea. For a given set of large-scale observable properties, every possible configuration of particles that could give those properties is equally likely. We call the specific combination of large-scale macroscopic properties the macrostate. Macrostates are entirely defined by thermodynamic properties like temperature, pressure, volume, and number of particles. For a given macrostate, all microstates consistent with its thermodynamic properties are equally likely. For some macrostates, there are lots of different microstates or arrangements of particles that lead to roughly the same thermodynamic properties, while other macrostates can be produced by only very few microstates. Now let us look at an example to understand the concept of microstates and macrostates. Here is a system with 25 particles. Each of the particle can have two colors, either green or blue. So there can be 2 to the power of 25 number of microstates, but there are only 26 macrostates. So we can see that many microstates give rise to the same macrostates. One more thing to keep in mind that if the system is left to evolve, it will eventually try out all possible microstates that are possible given the laws of physics. All particle arrangements will eventually happen. So if we look at the system at a random point in time, it will be in a completely random microstate chosen from all possible microstates. And what macrostate will it have? Probably the one that's consistent with the most microstates. Until now, we have been talking about particles' position, but let's change the approach. Each particle of the system can have position, momentum, spin, vibration, literally any degrees of freedom that the system can have. Instead of particles being distributed through position space, a microstate is really defined by how energy is distributed through phase space. The average distribution of individual particles in phase space defines the thermodynamic properties of the system. So, if we leave the system long enough, its particles and its energy will find its way into all the different forms that are possible. The vast majority of possible distributions of energy leave the system very close to a single macrostate, which is the state of thermal equilibrium in which energy is maximally spread out and temperature, pressure, density, volume have the values we expect from classical thermodynamics. Statistical mechanics tells us why large-scale systems have the properties they do, but how is it related to entropy? Ludwig Boltzmann figured that out too. The Boltzmann equation tells us that entropy is the logarithm of the number of microstates consistent with the current macrostate times the Boltzmann constant. So our smoothly spread out equilibrium system has a high entropy and our clustered one has low entropy. There are certain special microstates or special arrangements of particles that look highly ordered but are still consistent with our high entropy macrostate. For example, if we try to draw a picture or write words in phase space, this is where we get to a point of common confusion. Order is not the same thing as low entropy, and the second law is not always the tendency towards disorder. In thermodynamic entropy, the only special arrangements of particles that change entropy are the ones that change the thermodynamic properties. So, the macrostate that defines thermodynamic equilibrium is by definition the one with the most microstates, which also means the maximum entropy. Any system not in equilibrium must increase in entropy simply because at any future time its current microstate will most likely be one of the more common types of microstate if we don't force the system from outside. But if we use external force like using a vacuum pump and a glass wall to move all the air to one side of the room, we are reducing the number of accessible microstates, which by definition must reduce entropy. Heat must flow between the system and the outside universe in a way that increases the entropy of the universe as a whole. Statistical mechanics inevitably leads to entropy and the second law, and it does so by something so fundamental and basic. It comes from counting the ways that energy can be distributed. So the inevitability of the rise of entropy is as fundamental as counting. That's why Einstein and Eddington were so sure about it. But entropy is also statistical and emerges from the behavior of particles under the laws of motion. This is where the second law appears to add something new to the universe. It seems to add the arrow of time. Unlike the laws of motion, where Newtonian or quantum mechanics don't care about the direction of time, the second law of thermodynamics clearly distinguishes between the past and the future. It's almost like the concept of time is emergent and statistical, just like entropy again. We will talk more about information entropy and black hole thermodynamics. Till then, keep your number of accessible microstates low, avoid thermal equilibrium, and keep being in the brilliant macrostate. Thank you for watching. Hope you liked this. Please like and share this video, and to see such videos in future, do subscribe.